All right, section 5.2 is going to deal with a couple things. It's going to deal with state functions and enthalpy. And state function, we're going to start first with state functions, then we'll progress on to enthalpy. But those are kind of the two major topics that we're going to study in 5.2 when we talk about thermal chemistry. Now, state functions. What is a state? Well, a state is, remember, what state of matter something is, whether it's a solid, liquid, or gas. And up until this point, we've kind of, when we've done chemical reactions and everything else in chemistry, we really haven't given much attention to whether it's a solid, liquid, or gas. But now it is going to be a huge deal. And the reason is because some of these things, solids, liquids, and gases, have different properties or different values or different energy values. And when we start talking about chemistry, there's a huge difference between a solid, liquid, and gas in a molecule. So a state function is something that is dependent on its state. The value is dependent on its state. Now, there are going to be slides on this lecture today which aren't necessarily important. I'll do my best to point out which ones are not of significance. This one really isn't much of significance, other than a state value. A state value is dependent on the phase of matter which we're dealing with. Our state function is very important on the phase of matter that we're dealing with. So, where do we get a state function? Typically in a system, if I go from a solid to a liquid to a gas, and I heat up a liquid, it's too difficult to kind of figure out the internal energy of that system. So it's very, very difficult to figure it out. So it depends on the state of matter, not the path at which the system arrived at that state. So state functions, again, the big thing with state functions is it's dependent on what the phase of matter is. It isn't very important whether it's a solid, liquid, or gas. There are certain properties in chemistry which the values are dependent on whether it's a solid, a liquid, or a gas, and that is a state function. That's the definition of a state function. Q and W are not state functions. All right, think about it. The amount of heat I add to something is not dependent on whether it's a solid, liquid, or gas. The amount of work I do on an atom or an element or a compound or a reaction is not dependent on the amount of whether or not it's a solid, liquid, or gas. So Q and W are not state functions. So that is kind of important here. This is the important thing here. Q and W are not state functions, but we're going to talk a little bit about state functions here in a second. So Q and W are not state functions. That means the work and heat are not dependent on the phase of matter, solid, liquid, or gas. So work. Let's talk about work again. Work in an open container, the only work done by a gas is the pushing on its surroundings. So if we have a piston, really, a gas enclosed in a container, the only work is done is the gas that's pushing that container. Wow. Well, now what we have here is if we push in a container, in an open container, we have two keys at work here. We have pressure, which is the pushing down, and then we have the change in volume. As you can notice here from the pressure, all right, over, this is the change in volume. So it took pressure to push it down, and then the piston changes in volume. And that is work. When I'm pushing down on that piston, I am doing work. So when we're talking about a gas or the surroundings of pushing down on a gas, I'm doing work through pressure and volume. So what we can say is the measure of work done by a gas in a vessel, we could say work is equal to change in negative P negative P times the change in volume. Now we had work is force times distance. All right. However, we can also write work as negative P times change in V. Now, that's going to help us kind of establish a couple things as we move forward here. It's going to help us talk about enthalpy. And enthalpy is kind of that second law of thermodynamics. It's kind of the big thing in thermodynamics, the second idea. So the idea of enthalpy, if a process takes place at a constant pressure, as the majority of things do, right? If I do a chemical reaction in this room right now, does the pressure in this room change at all? Absolutely not. So the pressure rarely changes. The only work done is the pressure volume work. And what they mean by the pressure volume work is, remember, work is equal to negative P times change in V. Right. So it's hard to kind of figure out the heat flow. So what is enthalpy? Well, enthalpy, first things first, enthalpy is abbreviated with an H. So enthalpy is abbreviated with an H. Enthalpy is the internal energy plus the product of pressure and volume. So enthalpy is really the internal energy. Enthalpy is the internal energy plus the product of pressure and volume. So we can use what we know about energy, work, and heat to go ahead and figure out enthalpy. So if we look at this idea of enthalpy, when the system changes, right, this is our equation for enthalpy. Change in H, which is enthalpy, is equal to energy plus pressure times volume. This is everything that's been given to us already. This was the definition of enthalpy. However, we can write this as kind of this. We can change it, and we can separate it out, and we can get the change in enthalpy is equal to the change in energy plus pressure times change in volume. And that's what the rule of enthalpy was saying. The enthalpy is equal to internal energy, which is change in E, plus the pressure volume product in the sample. Now, what we're going to be able to do with this is we're going to be able to substitute a couple things and simplify what H is, or what enthalpy really is, in an equation. So we know change in E is equal to Q plus W. So let's go ahead. We can take change in E and plug in Q plus W. We know W is equal to negative P times change in V. So simply by changing over the negative, we can sub that P change in V is equal to a negative W. Well, what's Q plus W minus W? That simplifies our equation as change in enthalpy is equal to Q. So at a constant pressure, the change in enthalpy is the heat gained or lost in a system. So why do we study enthalpy? Well, in thermodynamics, we're studying the energy in a system. The importance of energy in a system deals with whether or not heat is gained or lost. And that is what enthalpy is. Enthalpy, change in H, is our heat gained or lost in a system. And we can calculate that for every single product or every single chemical reaction we ever do. We can calculate enthalpy. So, real quick here, we talked about endothermic and exothermic in 5.1. We can review again. A process is endothermic if it's positive. So if change in H is positive, it's endothermic. Likewise, if change in H is negative, exothermic. You are going to want to remember those processes for the remainder of the year. H is positive. When H is positive, it's endothermic. Heat is entering the system. And when change in H is negative, it's exothermic. Heat is exiting the system. We are going to kind of study the enthalpy of a reaction. So if you want to figure out what the enthalpy of a reaction is, whether or not it's going to give off heat or heat will be lost, here's the equation you want to use. Change in enthalpy, or change in H, is equal to the enthalpy of the products minus the enthalpy of the reactants. Put those two together, that gives you the change in enthalpy. So, real quick here, we talked about state functions. State functions is a function that is dependent on the phase of matter, whether it's a solid, a liquid, or a gas, makes a difference. So a solid, a liquid, or a gas makes a difference for certain properties. All right. This quantity, and then we talked about enthalpy. So we have states of matter, state functions, and enthalpy. Now enthalpy is called heat of reaction, and it's abbreviated change in H. So enthalpy is change in H. One couple last facts about enthalpy. Enthalpy is an extensive property. So remember, extensive properties are properties that depend on the amount of mass present. Change in H in a reaction for a forward direction is equal in size, but opposite to the sign if it's reversed. So what that means, what step 2 means is, remember, reactions can go forward or they can go backwards. And if the enthalpy for the forward reaction was positive 100, if the reaction goes backwards, it would simply be a negative 100. And that is what that means. And lastly, enthalpy is a state function. Enthalpy depends on the state of the reactants. So why is it important to start focusing on whether something is a solid, liquid, or gas? Because when we start focusing on enthalpy, enthalpies matter whether it's a solid, liquid, or gas. So enthalpy is the amount of energy in a reaction. A very important function to understand is the amount of energy in a reaction. The heat gained or lost in a reaction is enthalpy. And enthalpy, again, is change in H. So we will continue to focus on enthalpy and the importance of enthalpy and the importance of state functions. And remember that state functions are functions that are super dependent on whether it's a solid, liquid, or gas, and enthalpy is kind of the first one of those terms that we learned about.